My name is Lana Yuganova, and this event is organized by the Natural Language Processing Special Interest Group. Given the interest that ChatGPT has generated in the last few months, I'm sure we're all impatient to get to the contents of this talk. Today, we have two wonderful presenters to share with us and address various aspects and applications of ChatGPT. They are both scientists in Dr. Zhiyong Lu's research group at National Library of Medicine at NIH. Dr. Shubo Tian, he will start us off. He holds a PhD degree in statistics and has a wide range of experience in research and industry. His current interest is in using pre-trained language models for various biomedical and clinical applications, including information retrieval and information extraction. Our second speaker is Dr. Qiao Jin, who, interestingly, before shifting his research interest to computer science and medical informatics, he has obtained a MD degree from the Tsinghua University in 2022. Dr. Jin's current research interests include deep learning, natural language processing, information retrieval, and their applications in biomedicine. He has won the first BioBank Disease AI Challenge and the TREC 2020 Precision Medicine track. His work on EBM-Net received the Best NLP Paper Award from the International Medical Informatics Association in 2021. And his primary focus recently has been to improve biomedical information access with large language models. Before I give this to Dr. Shubo Tian, I want to share with you that on the videocast link, there is a button that says live feedback. Send live feedback. So you can use that button to send your questions, as we do expect that you will have a lot of questions. There will be a 10-15-minute time at the end of the talk to answer these questions, and we will receive them and read them out to the speakers. And with that, I'm happy to turn this to Dr. Shubo Tian.
Hi, good afternoon, everyone. So thank you so much for having us here, and thank you for joining this talk. My name is Shubo Tian, and today, Qiao, my coworker, and we together are going to talk about ChatGPT and some other large language models and their applications in biomedicine. So ChatGPT has been such a hot topic in the last couple of months. It acquired more than 100 million users in the first 2 months. And the daily visits to OpenAI's website hits more than 30 million. And if we search ChatGPT on PubMed, we can find articles containing ChatGPT that were added to PubMed doubled every month in the last 5 months. So today, we're going to look into how large language models like ChatGPT, how they're created, what capabilities they have, and how to unlock their powers, as well as how to adapt these large language models for our biomedical applications. Before we dive into the details, first, let's look at what is a language model. So a language model is a model that computes either of these two probabilities given a sequence of words or tokens. So the first one is the joint probability of the whole sequence, or the probability of a word conditioned on its previous words or tokens. Let's look at this example. We have this sentence. We want to compute the probability, the joint probability of this all the words in this sentence. We can compute this probability is equal to the production of each word conditioned on its previous words. So this is what a language model is. Language model has been an important research area since 1950s. And the first natural network language model was introduced in like 2001. And after the transformer architecture was introduced in 2017, it became the fundamental architecture for most of the recent language models. And depending on the specific architectures each language models use, they can be grouped into 3 categories. So here we can see, because the transformers include encoder and a decoder, language models can be built based on encoder only or decoder only, or include both the encoder and decoder. The encoder only language models include some models like BERT or its variants, and decoder language models include the GPT families and some others. The encoder and decoder language models can include models like T5 or the BAT. And since some researchers found scaling up language models lead to significant increase in their capabilities. So in the last few years, the size of language models has been growing. When we look at these different type of language models, encoder-only language models and encoder-decoder language models are usually trained using an inferring, or we can say a masked language model, or spam corruption objectives. And the decoder language models are usually trained in a causal language model or autoaggressive language model. And for encoder only and decoder language models, they're typically pre-trained using large corpus and then fine-tuned using some downstream task training data and then applied to the downstream task. But when GPT-3 was introduced, it demonstrated increased generalizability. So after that trained with large corpus of data, they can be directly applied to the downstream task without fine-tuning. So this has resulted in the recent development of the trend to developing more of these decoder-only language models. And we know, like GPT-3, it has demonstrated powerful capability in generate text, but sometimes they also produce some toxic or biased or harmful content. So how can we align these large language models to our human preferred content? A group of researchers, Yang et al., they propose an effective method to fine-tune these large language models to a human faithful language model. So they use 2 steps to fine-tune these language models. So after like GPT-3, after that pre-trained with large scale corpus, they collect some prompts from the API, and then they ask human labelers to write sub-spec content for these prompts. And then they use this data to fine-tune the pre-trained language model. And after they fine-tune this model, they collect, for each prompt, this model can output different contents. So they collect these different contents and then ask the labelers to rate which one is better than the others. And then they use those rated data to train a reward model and put them together to further fine-tune the language model using a reinforcement learning from human feedback. And this is how the ChatGPT and the InstructGPT was created. And after these models are fine-tuned, they become more faithful for human beings. And we know large language models like ChatGPT are very powerful, but how can we unlock their power? And this is how we can do. Yes, prompt engineering is the key to unlock their power. So we can correct some useful prompt and then feed them into the model and ask the model to output what we want, generate the contents we want. They say, hey, buddy, can you do something for me? And then, you have a prompt, say, this is what we want. And then because these large language models have very strong in-context learning, and they're able to output human-like text, so they can output what you want. And there are many prompt engineering techniques, and here are some of them. So some standard prompt engineering include this one-shot learning. So we have a task description and something we want the model to do. So we use this as a prompt and feed into the model and ask the model to output what we want. Or we can include some examples for the model to learn through the in-context learning ability. So if we have one example, we can call it, this is one-shot learning. We also include several examples as a few-shot learning and input them to the model to have our output. And for some complex question answering tasks, sometimes using standard prompt is difficult for the model to generate the correct answer. So in this case, a group of researchers, Wei et al., they propose an effective way called chain of thought prompt engineering. So in this case, in this example, if we just input the question and then have just input the answer is 11 to the model, and I ask the model to answer this question, usually they will give you a wrong answer. But if we ask the model, I say, let's reason step by step and input these reasoning steps, include these reasoning steps in the prompt and input it into the model, and the model will also generate the intermediate steps and then generate the correct answer. So we know large language models like ChatGPT are very powerful, but how can we adapt them for biomedical applications? There are many skills, many strategies we can use, but these are the main strategies. Now you can use any one of them or a combination of some of them to adapt the models for our biomedical application. We can train the whole model from scratch, like these models like GetChain or GPT, or we can initiate a model from the pre-trained general language model and then further pre-train them with biomedical corpus, or we can directly use the model and then do some task-specific fine-tuning to adapt them to a specific task. And for some large language models, it's pretty difficult or very expensive to pre-train them or further pre-train them. In this case, the easiest way is to use prompt engineering to teach the model to generate what we like, or we can do some use some soft prompt technique to fine-tune the prompt. Or if you want to adapt the whole model to the domain, we can create some data and then fine-tune the model. So these techniques more expensive than these two. And this will update the whole model's parameter and make it more better for adapt to the in-domain task. This tool is less expensive, but you will need to find the right one. So yeah, this is how we can adapt the large language models for our application. And next, Qiao will cover several applications of ChatGPT and large language models. So Qiao, please take from here.
Thank you, Shubo, for your wonderful introduction on the large language models. And for my part, I will cover 3 applications that are related to biomedical information needs. So first question, what are biomedical information needs? Well, as general public, we might have a lot of questions about biomedicine. For example, I might ask, shall I get a flu shot? This is a legit biomedical information need because we might want to know the benefits or the side effects of a flu shot, and it's very important to precisely answer this need. And sometimes we are patients and we might have some symptoms. For example, we might have a fever and a headache, and we might want to know, what shall we do? Can we just do some self-diagnosis and buy some OTC drug, or shall we directly go to the doctor's office in the emergency departments? So for doctors, clinicians, they might want to know the up-to-date guidelines to treat specific patients with some symptoms and past medical histories. And we also have information needs from researchers, scientists about the specific signaling pathways, mechanisms of diseases, and the drug targets. And also from the biomedical curators who are basically maintaining all these biomedical databases, and they want to know the new findings to update the, for example, gene entries in the database. Well, as you can see, there are various biomedical information needs, and it's very important to serve all these information needs. And this brings us to our first application today, which is the question answering task, or QA in short, because just as we discussed, information needs are naturally expressed by questions in natural language. So the process of answering questions is a process of serving information needs, and this is question answering. This task has been extensively studied in both general domain and biomedical NLP. And this is a hard task because it requires the model to have several capabilities to perform well. So first, the model needs to be knowledgeable, which means that the model should know something about biomedicine. For example, a patient might come with a list of symptoms A, B, C, D, E, and the model needs to know what diseases are associated with each of the symptoms. And this disease-symptom relationship is just one aspect of the biomedical knowledge that the model should possess to perform well on this task. And second, the model should do reasoning well, which means that the model should understand the context of the question, the context of the information needs. Well, for example, Siri is very knowledgeable, but it often fails because it cannot understand your question. And this is especially true in biomedicine because, for example, patients, they might come with a long question with a lot of non-standard terminologies. For example, a patient might say, hey, doctor, I'm not feeling well, and I started yesterday when I was eating with my daughter, and blah, blah, blah. It's a long story, and after all, there's a question. And it's vitally important to understand the whole story, the whole progression of the disease to precisely answer the question. And besides knowledge and reasoning, the model should also align with human values. So what is alignment? Which in the case of biomedicine, for example, patients might ask very basic questions. For example, what does this blood glucose mean? And as a knowledgeable AI model and can do perfect reasoning, the model cannot say that, why do you ask this basic naive question, or your question is too naive? This is not helpful. And this actually does harm to the patient. So instead, the model should say that, well, blood glucose is a measure of sugar in your blood. So in this case, the model is really helpful and aligned with human values. And the performance of NLP model is measured by standardized data sets. And if I only have time to introduce one data set for biomedical question answering, and that data set would be the PubMedQA US EMNLP data set. This is perhaps the most widely used biomedical data set for evaluating large language models. And as you can tell from the name, it's US EMNLP stands for the United States Medical License Examination. So examination data set, where for each instance, you have a question that's the description of the patient, and you are also given 45 possible choices like A, B, C, D, E, and your task is choose the right choice from all the possible choices. And after you have the model prediction, you compare it with the ground truth answer and get the accuracy score, and that is the performance of the model. And let me show you a concrete example from the US EMNLP data set. So this is a question, and the question is basically a description of patients, 27-year-old HIV positive female gave birth to a baby girl, and the lung context. Then the question is, which of the following assays should the hospital use to detect something? And the four choices, ELISA, HIV antibody, and the PCR and Dalton. So you should input the entire question as well as the four choices, the whole thing, to a large language model. And besides it, you also need to input this famous chain of thought instruction. Let's think step by step to the large language model. Because if you do not input this sentence, the model will directly say, well, the answer is B. Well, that kind of answer has a higher error rate. But if you input this instruction, the model instead will reason from the very beginning, from like the first principles, and do a long reasoning chain because something isn't something, and so the answer is something, and that has a higher success rates. So, and as you can tell from the question, there are two requirements to answer this correctly. First, knowledge, which means that model needs to know what ELISA is, what HIV is, and what PCR is, so on and so forth. And the second, model needs to do reasoning because, you know, it's a long question. Even for me, I spent some time to comprehend what's the information need in this question. So knowledge and reasoning. And this is an example of the text generated by large language models. So large language models, their core capabilities to generate things based on something. And in this case, before the orange bar, you input everything to a large language model. And after this orange bar, everything is generated by the large language model. And as you can see, the first word is about how HIV infection works. And the virus enters the body and begins to replicate in cells. So it's like really reasoning from the first principles and step by step. It's a long reasoning chain. And after all, the model says, therefore, the answer is C, which is a correct answer. The model does well on this question. Well, that's just one question. So what's the performance of our questions in the test set? Before we talk about that, another good thing about PubMedQA dataset is that it's also a standardized task for humans, so that we have human scores. We have two scores: the human passing score, which is 60 out of 100%, and this typically, for example, a medical student would have this score. And we also have the human expert score, which is like 87, and from, for example, an experienced doctor, and we can guess what's the best model's performance. But the model is not a large language model. That's before the era of large language model. Well, you can tell from the arrangements of these bars, because this is the leftmost bar, so it should have the lowest performance. And actually, the performance of this model is 47, achieved by a model called Dragon by Stanford. And this paper was published in Europe 22. So this is a really great model, beautifully designed, state of the art, but it only had 47. The score is way below the human passing score. And then we entered the era of large language models. And the first model is GPT 3.5. This is basically ChatGPT. And the score of it is just slightly above 60.2 or something, but it already created a lot of news pipelines, basically saying that ChatGPT passes the USMLE test. And this is really a huge leap, given that the previous best model is only 47, and you bypass all the 50s, directly going to 60s. So huge leap for the first large language model. And then we have the MedPalm model. So PALM is Google's Pathways language model. It's Google's counterpart for GPT-3, and MedPalm is a medical version of PALM. So the performance of MedPalm is like 67 something, and it's definitely an improvement over GPT-3, but it's still in the 60s. And then we have GPT-4, which is a much more capable version of GPT by OpenAI, and its performance is like 82 something, and you can say it's a huge leap from MedPalm to GPT-4 because you bypass all 70s and directly going to 80s, which is the same level as a human expert. And after GPT-4, we have the MedPalm 2. So Palm 2 is Google's counterpart for GPT-4, and MedPalm 2 is a medical version of Palm 2, and it has further improvements like performance going to 85. So now the performance is really close to the human expert score of 87, and I'm pretty sure that in the near future, large language models will definitely surpass the human expert score, because everything from the first large language model to the current best, it happens within half a year. And given that it's from the human passing score to the human expert score, it takes tens of years for humans. It's just half a year for large language models. So it's a huge improvement. And let's go to our second application today, which is the summarization task. So unlike question answering, where you give a question to large language model and directly gets an answer, for summarization, you not only need a question, but you also need to give the model several articles or documents for the model. And the model will summarize the provided articles or documents to answer your question. And as you can imagine, there are multiple scenarios in biomedicine where summarization works. For example, you can use large language models to summarize medical evidence. Basically, you provide this randomized control trial articles, one of them or a collection of them, to a large language model, and then large language model will summarize this RCTs. It's basically automatic evidence synthesis. It's like they are providing a draft of systematic reviews for you, and that's really helpful. And some people also argue that ChatGPT might be the future of discharge summaries, because these discharge summaries are basically summarization of all previous clinical notes. And you can also apply these large language models to radiology reports. You can use it to combine the predictions of different image models and generate a single report. And based on this report, you can interact with patients, answer patients' questions. For example, patients might ask, what's my diagnosis, what's the prognosis, and what medicine shall I take? So there are many scenarios where summarization helps. Well, we talk about how large language models can do question answering, can do summarization. However, they still cannot serve some information needs well. For example, if I ask this question to ChatGPT, please list basically symptoms of long COVID. And I also ask it to cite source article titles and their PMIDs. And here is the response from ChatGPT. And as you can see, this whole response is looking very plausible, because the list of symptoms and, for example, fatigue, muscle weakness, and you also have the source article titles, and also have the PMIDs that are 8 digits. They look really real, even for me. But if you carefully verify everything in the response, you will find that basically most of the article titles are totally fabricated, and all the PMIDs, they exist, but their articles are not relevant to the listed symptoms, which means that large language models basically make up everything in the response. And this is a huge issue, and this issue is known as the hallucination issue in the literature. And this indicates that you cannot directly use a large language model as a search engine. But the good news is that there are multiple ways that we can tackle the hallucination issue. And the most obvious way is called retrieval augmentation. So in this retrieval augmentation, we are basically combining a large language model and a search engine. Well, you can think of the case of the new Bing, and I will give you an example of ChatGPT with the web browsing plugin, where I basically asked this question. So which movie won the Oscar award this year? So as you may know that ChatGPT, the training data is before mid-2021. So this is not in the training data of ChatGPT. But if you allow ChatGPT to search the web using a search engine like Google or Bing, you can search your question and get the retrieval list of relevant web pages from that search engine. For example, list of articles, list of news, and ChatGPT can also read all the text in that news, and based on the text, answer your question. It's like they are provided with relevant documents to your question, and this task suddenly becomes a summarization task, which large language models do pretty well, extremely well. And for this question, ChatGPT with the web browsing plugin answers my question correctly with this reading content feature, and cites the right article that is a news from CNN. So we can do the same retrieval augmentation for the previous example of long COVID symptoms. Basically, we actually propose a trilogy of retrieval, summarization, and verification for literature search with the help of large language models. And the first step is retrieval. So it's super easy. You just provide relevant articles of long COVID symptoms to ChatGPT. You just need to collect their titles, their abstracts, and these articles, you can find them through PubMed or any other search engine. And this is the first retrieval step. And the second step is summarization. You basically input your question and all relevant documents to ChatGPT. And then ChatGPT will summarize these documents to answer your question. And in this case, ChatGPT does a much better job compared to the previous example of fabrication. It provides a list of symptoms extracted from the provided list, and all these PMIDs are also chosen from the provided list, and they are relevant to the symptoms. So it does a much better job, but you still need a third step, that is verification, because if you carefully verify them, there are still some issues. For example, some symptom combination can be improved, and some listed items are not actually symptoms. So you still need to verify the output before you can actually use it. But I would say these are not fatal errors like fabrication. And as models improve, I think they will make less this kind of errors. But overall, we think the trilogy of retrieval, summarization, and verification is the future of biomedical literature search with the help of large language models. Well, even with retrieval augmentation, you still cannot answer some questions. For example, this question, what is the gene associated with the SNP? This one, I asked it to ChatGPT with web browsing plugin. ChatGPT says that it seems that there's limited or no public information available for this specific SNP. Well, why? Because surprisingly, all these commercial search engines like Google or Bing, they just do not index the specialized databases maintained by, for example, NCBI. In this case, the DBSNP is not indexed by the search engines, so you do not find anything from the web. What you will need to do is you need to use the specific database, in this case, DBSNP, and you need to find the SNP page in that database, and you need to check out the gene name of the SNP and get answer LRC23. That's the gene you are looking for. Well, this might be obvious to you, but for a lot of beginners, for a lot of laypersons, they don't even know that this database exists. And as you can imagine, there are hundreds of thousands of biomedical databases in the world scattered on the web. And what if we can teach large language models to use all these biomedical databases, and given a user's question, the model automatically tells which database to use and how to use the database and provide the answer to user's question. And for this, we propose a two-augmented large language model called GPT, where we are basically teaching large language models to use NCBI web APIs. And with the NCBI web APIs, you can access all the biomedical databases maintained by NCBI. For example, DBSNP, PubMed, ClinVar, OMIM, so on and so forth. And you can also use all these bioinformatics tools offered by NCBI, like the famous BLAST tool for sequence alignment. And let me show you a concrete example. So for this question, what is the function of the gene associated with the SNP? This one, let's decompose the question to sub-questions and solve them step by step. So this is a harder question than the previous one because it's a multiple question. You first need to get the gene name, and then you need to get the function. And this is the output of GPT. It first decomposes the question to two sub-questions. And the first sub-question is, which gene is this SNP associated with? And GPT knows that for this question, it needs to consult with, it needs to use the database tool, and it generates a URL, which we call the web API request. And basically, if you click this URL, you will get the raw outputs of everything on the SNP information page. And we just help execute this API call and append the raw information to the model context and let GPT continue generation based on the API call results. And GPT gets the correct answer, which is LRC23. And it then asks a second sub-question and calls another API and finally gets the right answer. So this shows that besides a search engine, you can also augment large language models with domain-specific tools like database utilities and to provide improved access to biomedical information for the users. And that's the three applications I talk about. First is question answering, where large language models achieve state-of-the-art performance close to human experts. And the second is summarization, where you can find multiple scenarios in biomedicine that is useful. And the third is information retrieval. Although you cannot use large language models as a search engine, you can combine large language models with a search engine, like in the case of Bing and ChatGPT browsing feature for retrieval augmentation. And you can also combine large language models with domain-specific tools, like in the case of GPT and ChatGPT plugins for improved access to biomedical information. And that's for my part. Thanks. Okay, let's welcome Shubo back for more introduction of the applications.
Thanks, Qiao. Yes, I will continue to talk some other applications. Let me share my screen. So the next one I'm going to talk about is about information extraction. So information extraction is a task to extract some biomedical concepts and their relations from some biomedical text. So this is a very important application which can be used to support about curation for biomedical knowledge discovery. Traditionally, this task was formulated as a token classification task or sequence labeling task, as we predict each token into a concept or not. And after we do that, we extract some representation of a pair of concepts and then predict them into a relationship. And traditionally, this task use encoder only language models for this application, but some researchers also is brought to use some decoder language models for this application. But from here, we can see the performance of encoder language models is much better than the performance of decode-only language models. This is for name entity recognition. That's to identify the biomedical concepts from the text. And this is the same for relation extraction. Most of the language models used for relation extraction are encoder-only language models. And yeah, there's some research on using some decoder language models for this application, but still they are still underperformed compared to the decoder language models. I think why these encoder language models are doing worse than the decoder ones, probably because this language model this decoder language model, we usually formulate the task as a text generation task. So we input the whole text into the model and ask the model to directly output these biomedical concepts and that relationship. And there's some problems there. Sometimes they will just rephrase the outputted concepts, or they will just rely on the relationship between these concepts. So given some traditional evaluation metrics like precision and recall, probably that's one of the reasons for these decoder language models to underperform the encoder language models. But we believe, if we can correct some appropriate prompt or find a better way to apply these decoder language models like ChatGPT, probably we will be able to, to increase their performance comparable at least to the encoder language models. And the other application is medical vision and language models. This application can be used for this medical image classification or for radiology report generation. Usually, these models will include an image encoder and a text encoder, and then they're trained on some image and text pairs using a contrastive loss learning techniques. And several models have been developed, and these models are, because the clips, the contrast learning image pre-training language and image pre-training model demonstrate very successful for some image and text applications. So there are several models based on these clips learning techniques have been developed. This model usually use a vision model, like a vision transformer model or a ResNet model, and they use both some encoder or decoder language models as a language model to encode the text. And these models have been shown to perform pretty well. But as we can see, some large language models like ChatGPT haven't been explored for this application. But given this very strong text generation capability of ChatGPT or some other language models, we believe we can find the right way to use them together with some vision models that should be able to facilitate the development of these medical vision and language models. The last couple of applications are mostly natural language processing related, but large language models like ChatGPT can not only use for those applications, they can be used for some other applications like medical education or scientific research as well. Here we will specifically talk about medical education. So, we know these large language models like ChatGPT that pre-trained with large scale of text data, and they encode a lot of knowledge in the model, so they can serve at least as a knowledge base to provide some insights, or for some students to ask them questions, and then they can provide some explanation. Some models like ChatGPT, they also serve very strong conversational interaction ability. So, if we can use these models to develop a more interactive learning way or learning environment, they will benefit these medical students too. But use these models for medical education. They also have some of the cons. As Qiao just explained, they can hallucinate. So they may produce some counterfactual or wrong information, or the results output from these models may not be reliable, or although they encode a lot of knowledge, including some clinical or medical knowledge in the model, they're not able to capture the full complexity of this knowledge, or the field decision making process for some clinical application. So these are all the applications we talk in this talk in the biomedical domain. Now, although these language models like ChatGPT, and they're very powerful, but they still have their limitations and impose some risk. To train this model is very expensive. They can produce some wrong information. They can impose some safety risk. But the most relevant to biomedical and clinical applications, we believe, are the bias, inherited by these models. This bias can be gender bias, can be race bias. Some research already find some language models have some anti-Muslim bias. We know in some clinical applications, some groups, these different genders or races may be biased. So when we use the context to train the model, they will make the model biased too. And the harm of this bias can include, they can produce some disparity of service qualities, or some discriminations towards some certain groups. Qiao already talked about the hallucination risk, and this is even critical for large language models, because with their increased capability, they're able to produce more believable or convincible content. So, when we're using these language models, we need to take some, especially higher cautions. And privacy, this is also true. In the data used to train the model may include some individual personal information. Some researchers already they can identify some individual information from these language models. And when this language model used for some clinical application, they have access to some patient's personal data. So this could impose some risk to the individuals. And when we use ChatGPT for some research and use them to help for manuscript writing, they also cause some kind of authorship issues. Some journals already banned listing ChatGPT, I think also. And this is some risk and limitations. We believe we need to take caution when we use ChatGPT or other language models for our application. And although these models have their limitations and risks, but we believe if we can use these models properly, we should be confident to have a vision that we can develop some kind of generally more AI models for our applications when we're looking forward. And this is the work of our group. And we'd like to thank all our group members I'm not going to read their names one by one. We thank them for their contributions and helps. We thank especially Dr. Lu for his advice and supervision. And this is what we talk in this talk. And we're ready to take questions.
Thank you so much, Shubo and Qiao. This is a really hot topic because I have received dozens of questions. And so if I will start asking the questions in the order they have received. We apologize, we won't be able to get to all the questions, but I may take a liberty to promise that we will try to get to your questions by email if we don't get to them in the live video presentation today. And also, so some people are joining us from Zoom and most people are joining us from Videocast. As I said, from Videocast, there is a button to click to send your email question. If you are joining us from Zoom, please do not unmute yourself. Rather, send your question to the email that has been provided. So with that, I will start with the questions. So I have a few questions that are in the category of Jin GPT. Qiao, so people are congratulating with the Jin GPT, and the question is, will it be publicly available? Are you planning on deploying it as a plugin? And how can people engage with that application?
Okay, so thanks for your interest and the great questions. The first questions, will it be publicly available? The answer is yes, we will release the code and you can replicate everything on GitHub. And the second, will we write a plugin for ChatGPT or make it deployable? We are not quite sure because if we want to do that, we might need to call OpenAI's API ourselves, and that model has been deprecated. So that also costs a lot of money. So we are considering that, but we're not sure. And what's the third question? The third question is?
So that was about Jin GPT. So we will be able to provide a way for people to use that tool, correct?
Yes.
Yeah, wonderful. So we will, as soon as that's available, we can send that link through our natural language processing special interest group listserv. So please be on the lookout. Another group of questions is about the controversial answers or questions that have conflicting answers. So people are wondering, how is ChatGPT defining how to answer it? So do they present an average answer, or is the system able to recognize differences in understanding? Can you address that? The questions that can have controversial answers or conflicting answers. What is your, what is your take on that?
Shubo, do you want to answer this question?
Yeah, sure. I can provide some comments. These language models are trained on very large scale of text, so they learn how to produce the output from what they learn, on this text data. It's very difficult to say, if they understand or not. Somehow, yes. We use the data to train the model, and the model was learning in a kind of. It's kind of, when we convert the data, this text data into numeric data and then do the computation, somehow they learn something, but it's very difficult to verify if they really learn or not. So they learn to produce. We just talk about the language model, so they learn to produce a text. The probability of producing some text from what they learn. So they may produce different texts from the model. Yeah, so this contents may be conflict. But Qiao, maybe you can comment more.
So from my understanding is that if there is conflicting or contradicting evidence, especially in medical literature, for example, whether melatonin is good for your health, let's say there are articles saying it's good, there are articles saying it's bad, and theoretically, if you train your language models well on all these articles, everything will be in the memory of the large language model. And but the answer actually depends on your question. So if you ask this question differently, you will get different answers. And if I'm going to do that, I will try to ask questions in various diverse ways to get many answers, many diverse answers, and basically and check their average and get the results. Also called like self-consistency prompting. So everything is in the memory. It just depends on your question.
Thank you. Thank you for that explanation. I have another question, which says, it is well known that GPT and large language model technologies are prone to hallucination responses, and I know we addressed that a little bit. So what steps are being taken to ensure that trustworthy information is being delivered?
Another great question. I think they ensure this basically, generally speaking, safety and the privacy and this kind of issue. First, in the pre-training step, they filter all these bad sources, like really bad messages on Twitter. They just filter all this information. So their training set is kind of clean. And this is the first step training. And then they will do what's called reinforcement learning with human feedback. So they are basically teaching large language models how to respond a question properly. And that's taught by human labelers. And that's the second step of controlling that. And there can be high-level layers built upon this large language models. Like you can have a model detecting whether a large language model outputs something bad, and you can just decide not to show that, like in the case of Newbin. But there are many ways, and the people are actually addressing this very seriously.
Okay. One question that is more on a general, more of a general question, and I just want to say that it's 3 o'clock now, so we officially are done with the hour, but our AV team has allowed us to extend this for another few minutes. So if Shubo and Qiao, you are available for the few more minutes,
sure.
Maybe we can cover a couple more questions. Okay. So how do you guys think this ChatGPT will change the general landscape? For example, young people who are going to school now, who are starting their college, and they are confused in terms of how will ChatGPT influence careers? Will that career be in demand in the next 5 or 10 years? Do you have any idea? What is your vision of the future, let's say in 5-10 years, which careers or how can it affect the choice of career for young generation?
So would you take first?
Do you want to answer this, Shubo?
Yeah, I can take it, and maybe you can have more comments. I would say, if we look at like ChatGPT, they're very powerful to serve as a knowledge base. So if you're looking for a job, it's more like supportive job. Probably you will have a large impact. And if your job is more decisive, so you need to verify all the information and then make a decision on that, probably will have a less impact. And also we can see, or we already saw, ChatGPT already bring many jobs or many demand of prompt engineers. So how to explore or how to dig the knowledge from these language models also requires some skills. So I think this is what I see.
So your take on it is that some things will disappear, but other careers will open up, other opportunities will come up.
Yes.
Okay.
Yeah.
Okay, great. Thank you for your question, Qiao. So if ChatGPT is giving you a summary of long COVID symptoms and the PMID's titles are wrong, then where are those symptoms coming from?
Well, that's a good question. So I would say the large language models, if we look at from the first principles, they are trained to predict the next token in all the training materials. So it's like it has a fuzzy memory, and it just based on all previous tasks, it generate the next token that's most possible in the training corpus. And I would say if you frame your question like that, the tags generated by large language model are most likely to appear in the, for example, PubMed articles, but that doesn't mean that they are true. It just means that they have higher probabilities. They are more fluent, for example. So, and because you input long COVID, and maybe the model says COVID, and it just outputs some words associated with COVID. So it's definitely not that precise.
Correct. Okay. So maybe we can take a couple more questions and conclude with that. But one question, we have a bunch of questions that are on privacy. Clearly, as we know, like hallucinations and privacy are one of the most issues with ChatGPT. So this creates a lot of interest. So how can we ensure privacy and security of sensitive patient biomedical information while using ChatGPT? And this is quite a general question, so I guess we have to speak about certain uses of ChatGPT. How do you use it? But can you say anything towards that? So how can we ensure privacy and security of sensitive patient information?
Yeah, I can provide some comments on here. Privacy is also that many research are being done on this issue. So, when we're trying to use clinical data, or this medical data, a lot of research have been done to deep identification, on the identification of this information. So, we at the beginning, when we have this data, we develop some language models to identify this personal individual information, and then just remove them or replace them with some different data, or have some shift, like the date, the age. We just shift them to a certain number. So I don't think it's possible to totally, resolve this problem, but with these techniques to the identification and with some care when we're using these models, it should be better.
Thank you, Shubo. And I have one more question that is related to Gene GPT. So it's with NCBI databases, there's less cohesive text for LLM algorithms to learn from. The scientific databases look disjointed with lots of symbols, numbers, table format, etc. How can models like ChatGPT systems learn from scientific databases effectively? Is LLM the best choice, or maybe other models can be added?
Well, that's an excellent question. And we actually did a lot of prompt engineering to make Gene GPT possible. For example, we not just input the user's question in Gene GPT, we also input a lot of in-context exemplars to Gene GPT. It's like we are showing Gene GPT how to respond to different kinds of biomedical questions, and how they can use the NCBI tools in the context. Basically, we provide all these examples in the input to the large language model, and in that process, we are teaching the large language model to use NCBI web APIs. But if we do not input all these exemplars, they might fail as you might expect.
Thank you very much, Qiao. So I think it's time to wrap up our meeting. Thank you, audience. Thank you, everybody, for joining us. Thank you, Shubo and Qiao, for giving this very exciting talk and for taking all these questions. We will try to get back to as many questions as we can. Please email us your questions. You can continue emailing, and see you at the next meeting. Goodbye, everybody.
Goodbye.
All right.
Thanks.